This is Bruce Carlson of Carlson Software. I would like to show you Precision 3D Culverts. It's a new program for determination of watershed boundaries, peak flow, and for sizing pipe culverts that operates fully in a 3D environment. And yet, as you're going to see here, the output goes back to CAD for standard deliverables. You can also produce a PDF report that I intend to show here. But let's first talk about why we see so many different textures. What's going on here? Did this take a lot of work? And the answer is no. The textures are mapped to colors in the Carlson tint file. If you go to Tools Settings, the fifth tab, Texture tab, you can see how the textures at right are mapped and correspond to different selections of colors. And that's user defined 100%. So RoadNet outputs a tin, but the tin has an extra attribute. The Carlson tin has a color attribute. Because RoadNet knows that edge of pavements are distinct from shoulders, are distinct from cut and fill slopes and high wall slopes, these are colored out distinctly, and the color in the tin, that attribute, is recognized by Precision 3D, and then through that mapping process is auto-textured. But other commands do the same thing. The Valley Pond routine found in Carlson Civil and in Carlson Hydrology will do a distinct color on the embankment, and that can be mapped to a texture. Same with Design Bench Pond and Design Pad Template. Now, in addition to that, you can draw a polyline and texture any area you like. If I placed a polyline at this high point here, hit C to close, I could select the texture tab here and drag and drop any texture of choice into that area. So you can texturize your site, but the only advantage of textures is quicker recognition of the site and the challenge ahead for doing hydrology design. Now we have stored, using the file save scene command, we've stored a scene that we've loaded here that had two different storm events that we were using for comparison purposes. A rational event with a 50-year return period storm, and an SCS event, type 2 24-hour, both with similar curve numbers 65 versus rational C coefficient of 0.65. Now they're not one-to-one in comparison, and you're going to see that in terms of the results of the calculation. We were focused on just this watershed above the embankment dam, and now that we're selected to the rational method, look to the right where the tooltips indicate the results of your design. When I hover over the water, I see both the subcatchment information as well as the pond information. The two items I want to focus on are peak flow of over 20 CFS, 21.894 cubic feet per second, and a pond volume of less than half an acre foot, really 0.386 acre feet, by the rational method. Over 20, under 0.4, those two numbers. But also the visual. Look at the visual extent of the pond that this 50-year storm by the rational method produces. If we double click into the SCS storm and make it active, the water area is larger. Well, that indicates a greater acre feet quantity, and sure enough, pond 4 by SCS had 0.7 acre feet. But the peak flow was only approximately 12 CFS, 11.938. Less CFS on the peak flow, you might have sized or undersized a pipe compared to the rational method in this particular scenario, this particular watershed, this particular length of flow, and other parameter aspects. So as the designer, you can try different scenarios, but within any given scenario, you can try different storm events, Not just SCS versus rational, but different return period years, 25, 50, 100, and different C coefficients, different assumptions, and then make your best design decision from that. You also have this wonderful visual feedback, even the aspect of moving water, which itself is a setting under tools. Show moving water is turned on. We even have show shadows turned on for uh, viewing through the water. You can kind of see the low point in the water better with show shadows on. Shadows degrades speed of operation, but not on a fast computer. You don't notice it. Um, so we've seen this observation on the effect of the two methods. Let's also study the rational for some other aspects. How did I come about selecting this, I guess, National Weather Service Maysville storm event? Where was that obtained from? Under Tools, Settings, on the very first System tab, you can select your rational rainfall library. And we've done that from a vast list of libraries that are common to Carlson hydrology. And these are stored in the Carlson project settings. And using the hydrology module, they can be created by you and added to or even edited. So if I go back to the hydrology module, and I've gone to Network Rainfall Libraries, you can see this is the actual file I've called up in Tool Settings within Precision 3D Culverts, and I've selected Maysville. So if I hit Maysville and edit, you can see the different year return periods and the duration. The intensity of the storm is higher at lower duration. So it's from these that Precision 3D, from the DTM involved, the surface involved, which comes in either as a Carlson 10 or a land XML file, which computes average land slope, length of flow, time of concentration, and most important is that time of concentration, here of over 9 minutes, from which the 6.9 rain intensity is interpolated, and it's different in different watersheds. Now we have a 5.4 rainfall intensity from that 50-year storm interpolated. Now volume is calculated differently using the rational method, and the volumes are shown when you hover over a pond and you see the overall volumes involved. And I would point out that there are three rational methods, three versions of the rational method as seen here, the default being universal rational. Okay, so let's do another observation of the already designed pipe draining under the road. This pipe was designed with a head wall, probably using this option here, which is pipe and head wall all at once, which we're about to apply to a lower drainage basin. The magenta line represents the overflow. Note the water would overflow at this magenta line and continue down the roadside ditch through that gate right there. And the actual pipe that was designed here was sized perfectly such that its headwater was this yellow line, which means that at this peak flow in this watershed, the water does not exceed this calculated headwater line. Let's click into the pipe culvert and watch the Property Explorer update the information. There's that discharge of 92 CFS handled by this 36-inch pipe, but with a headwater of, right here, 8.652. The program figured that out on its own. If you want to do your own study of it, calculate the flexible yellow headwater line by changing your pipe size. Well, obviously if I do a bigger pipe, it's going to pull the headwater down. 42-inch pipe, 42-inch pipe diameter lowers that headwater line. Still under sort of pressure, flowing full in inlet submerged or inlet controlled condition. If It calculates the optimum or most conservative of these three methods shown here: inlet, outlet, and another version of outlet. So I usually keep it on optimum to get the most conservative results. Some people actually dictate perhaps inlet control or outlet control in certain situations. Now, if we tried to second guess the program and said, 36 didn't work, why can't a 30 work? Try it yourself. 30, it immediately calculates the headwater at overflow. That would have overflowed and drained down the roadside ditch. That would be an inadequately sized pipe. So we'll put it back to 36 here, hit enter, and then we have that headwater condition that works. Well, let's do a dynamic calculation on this next pond, or this next low area on the north side of the road, requiring a culvert pipe for drainage. Just spin it around, bring it on over. But let's do a little work with our gate technology. We enjoy that phrase. What that refers to is sometimes watersheds are combined, particularly in large storms, with undersized pipes or no pipes at all, because the water reaches the overflow, continues on down, and if you did not pipe through this upper ponding area, you'd have to make a very large pipe to deal with the overflow from that area from the combined watershed. If you want to study this particular watershed, the one that I'm centered on right now, in isolation, double click moves in on the site. I'm double clicking, and I'm going to turn that gate by double clicking it to red. Red means don't consider above. But I'm going to do the same thing on the lower side of it. I'm using the wheel bar to zoom in and out. You can also control double click, and that does a zoom back. Let's double click this gate and fully isolate this center region here. There are other isolating mechanisms like maximum pond emerge, minimum pond depth, but we're going to focus on this area by using this simple approach of the red gates linking this low area only to this localized drainage basin. Now we're going to calculate the peak flow to that point. By the rational method, we'll do 50 year, then we'll add another storm event and do 100. Okay, the pipe is calculated, or the drainage is calculated, I should say. We haven't placed a pipe yet. Look to the right. Roughly 40 CFS, 39.42, rain intensity of 6.582. Now, one way to design a pipe in one step is to go to this fourth icon along from the left side up top, which auto creates the pipe and pushes it back to the head wall condition and places the head wall along with it. It finds the low point, it finds the yellow stick on the low points, and snaps to it. So I can just click there. As I go uphill, the pipe is yellow, warning me, and then I turn and go downhill and place the pipe maybe right there to try to minimize length a little bit. Then after I place it, I must select a head wall. I'll choose this North Carolina version. Just double click it. And then the program will go into a calculation mode, push the pipe back, place the head wall such that there's only a specified amount of freeboard behind the back of the head wall. Let's take a look. It just did it. Double click in, and you can see there's about 6 inches of freeboard in behind the head wall against that embankment. Let's do that control double click to pull back. And you can see it did a little riprap treatment on the outlet side, and that looks pretty good. That looks like you might just build it that way. You might have selected a head wall with a little bit longer wing wall condition to hold back the earth, but the small wraparound there would not impede on the drainage. I think that would actually work. So let's take a look at that culvert pipe. And that was culvert pipe, actually culvert pipe 2 here. And you can see that it has a length of 83 feet. Quite steep though, and on some of these steep pipe situations, some DOTs do not approve of concrete. They approve of corrugated metal, perhaps. Notice how the Manning's end changed automatically when we selected a different pipe material. And there we have it. The water has drained out. There's no water on the upstream side. And this barely worked. It's the smallest pipe size to keep that yellow line under the magenta. So a very close shave, you might say, on the pipe sizing. You might want to verify that that pipe is corrugated metal. One way of doing so is going up to the merge pond, clicking on the display tab, and turning on transparency. And now you can see, as you zoom in, that underneath that pipe is corrugated metal. So we even take the trouble of showing it to you as a corrugated metal look. Let's turn that off. And you can also look at the pipe by just simply going underneath and seeing it up close. You'll note that there's even a base below that red line to the head wall, and that's sort of its anchoring condition there in the earth. So we'll use the control double click, which quickly pulls us back. Now, that is how it handled the 50-year storm event. We know 100 years not going to work. So while we have this particular pipe sized here, and that is, let's see here, that's this design, and we'll take a look at its size under properties. That was sized at 30 inches. Okay, it's a 30-inch pipe placed under there. Let's just run a 10-year storm through it, just to show how multiple storm events can be output in a PDF report. How do we create another storm event? Here's how you do it. You come up here and right-click Storm Events. There's 2 of them right now. And you add a storm event. Go down and look for that newly added event. And it's number 3. It's active now. We'll click on it. Let's make it a type. Let's not make it SCS, but go rational again. Make sure you're clicked into Maysville. And we're going to make it a 10-year storm. So it'll interpolate differently on that rain intensity chart. And we'll go ahead and calculate. So this just takes a few seconds. And the peak flow on the upper side is 78, and it looks like we've drained the pond. It's past the condition. Just to be double sure, let's gate off both upstream and downstream gates. We're going to do that. And anytime you do any kind of a gate alteration or selection, then it is a worthwhile precaution to calculate the storm event again. And let's see if we've altered the peak flow by doing so. We're still dealing with the 10-year storm, and we move over here and see a peak flow. Yes, that was a critical aspect. We were dealing with a larger area before we isolated through the red gate technology there to the area in question. You can tell what you've isolated to, but when you move your cursor inside, the subcatchment that it will calculate with is highlighted in yellow, just as that embankment pond subcatchment Up there is yellow. Now we come to the one we're targeting, and it's now yellow. We're very certain that that is what we just focused on in the calculation. So we now have a 10-year storm event, and you can double click into the rational where we have a 50-year storm event. With both of these events calculated, go ahead and select the pipe you want to focus on. When you select a pipe, it highlights it. We want to highlight that lower one. There we select it. It's highlighted. You can change their names. I'm going to actually rename this one as Culvert Pipe 3 to be completely distinct. You have full control of naming. And now with that pipe selected, let's be double sure it's active. Culvert Pipe 3, it's active. Go and select PDF report. We can make your own PDF report form, and Carlson Software is happy to duplicate any pipe report form that you want to submit to us. But we have a generic one, Culvert Pipe Report Form, that I'll focus on here. I'll open that. And then this is the name of the PDF I'm going to output. I'll save that. And it's a 2-page report. Notice it has the correct lat long because I have that set under Tools, Settings, Projection. And we should have the 10-year column and the 50-year column filled out, and the other columns not, because we haven't addressed those storms. So you have the ability to produce a PDF report that can be modified using Adobe Acrobat or any PDF editor. And lastly, let's go ahead and take these 2 pipes that are designed here back to CAD to help us with the deliverables. So what we'll do is we'll go to File and we'll select Save to CAD. And we'll place this new file in C P3D webinar. We'll just put it there. And we can give it a name that we can easily remember. US 68 merge 5. I'll delete that portion of it. Just US 68 merge 5 and save it. Okay, we've done that. Now you can either exit or simply minimize, and back in the CAD at the command line, the command P3D culvert _ import will import that in, or you can find it in the pull down menus. P3D culvert _ import. This is coming along new between releases of 2015 Carlson and 2016 Carlson software, so it's only available on the very latest Carlson 2015, but it should be active with this command line entry in all cases. And we're going to go and look for the short name. There we go. Now we have our network pipe label settings, pipe network label settings. The program recognized there's in a sense, 2 pipes as part of the pipe network system involved here. I'm going to stick with the settings I currently have, hit OK, and now as we zoom in, you can see the results. We have a 36-inch concrete at 6%. We studied that one earlier. That makes perfect sense. We also have brought in the watershed information, pond information. The watershed information's in green, the pond information's in blue, and we even have the second pipe, which is 30 inches, and it is 82.08 in length, and there's the final results of that exercise. So we did the deliverable side of the equation, we did the PDF report, and we did the design in a 3D environment enhanced by the graphics and the feedback that makes the design fun and easy.